Okay, this is the next part of the run-through for this Pearson Edexcel IGCSE Physics paper from January 2023. So I don't know why they haven't written the year on the paper. Okay, during COVID they stopped writing it because I think once they cancelled an exam and then they reused it. So this is the January 23 paper. It's the paper called 1P, so it's the same for double award. So if you're doing the double award or if you're doing the full physics, this is paper 1 for full physics. So paper 2, physics students need to do, double award students do not need to do. There's also, as I explained before, there's also a regional paper 1, which I can upload as well if I get enough people liking and sharing the video to make it worth the time to do these recordings. So far not many people are watching them. I gave this as a practice run through, as a practice paper in a live session for my students, and then I put the answers up in 3 parts already for different topics that have been covered up to now. So if you find these useful, please provide feedback either by commenting, and to show your appreciation, make sure every video you watch, if you learn something from it, give a thumbs up, because that's how YouTube works. Otherwise people will stop making videos. Okay, so we've gone through 3 parts and I think we're on question 7, but I just want to show you that the last 2 questions had graphs in them. This is the question on radioactivity, which I think is question 4. So they're talking about a scientific method of taking the radiation, measuring the radiation, and then putting an absorber in front of it. So graphs are a big part of physics. And this is a smooth curve, so it's a decay curve. So you have to be able to interpret it and plot accurately. And then in the next question, question 5, another graph appears, and this time they're giving you the data and they want you to analyze stopping distance in terms of thinking distance and braking distance. So you need to really become good at analyzing graphs. So we went through 2 questions already with graphs in them, and you'll see that the next question, which is now going to be on electricity, will also have graphs in it. Okay? All right, so the next question is on electricity. Here it is. And we're going to go straight into it. A student uses the circuit shown in diagram 1 to investigate how the current changes with voltage for a filament lamp. Okay, so this is a very, very common question, and it comes from topic 2 in electricity, so you'd have studied it with whoever taught you in year 10. It's a big topic, okay? There's only 1 question on electricity in this paper. All right, so what do we have to do? So you see what's happening. There's a cell. You need to know these symbols, and you need to be able to draw them properly. So this is a series circuit, and you can see that the current flows. So this is the positive terminal of the cell, the big line, and the current's going to flow through here, through the ammeter, through component Y, which you need to label. That's a variable resistor. And then it goes through the filament lamp. Okay, so this is the filament lamp, and you'll notice that the voltmeter is in parallel with the filament lamp. So ammeters always go in series, yeah, with the component, and voltmeters are always in parallel. If you put the voltmeter where the ammeter was, it has such a high resistance that it would block the current and you wouldn't be able to do the investigation. So basically do everything in series first, and then because you're interested in the filament lamp, that's your investigation, you put the voltmeter in parallel across, which means in parallel with the component that you're investigating. All right, so it says give the name of component Y. So component Y is here. And you see this arrow means you can vary and the resistance. So the resistor is the rectangular block. Yeah, so resistor would just be a rectangular block. When it's a variable resistor, they put an arrow going through it. And that's the kind of thing that you use when you have dimmer switches in your homes. Okay, so that's the variable resistor. So that's a way of varying the voltage, because obviously the voltage of the cell here, this is voltage provided by the cell, is now shared between the variable resistor and the component that you're investigating. And depending on your setting of the variable resistor, yeah, if you put on a high resistance setting, then the bulb will get less voltage and the resistor will get more voltage. So you can vary how much voltage goes to the bulb. Okay? So it says, this is what they want to explain. Give a reason why component Y is included in the circuit. Okay? And the reason is to vary the voltage across the lamp. So if the variable resistor gets more resistance, it will take more voltage and there'll be less voltage left as the share of the total voltage for the bulb. Okay? So by varying the voltage, it also controls the current. As you'll know, the bigger the voltage, the bigger the current will be. Okay, so this is a very, very common question. They can give you a question like this on a bulb, a piece of wire, resistance wire, like a thin bit of copper wire even. And they could also give it to you with a diode. Okay, a diode has a special relationship. Okay, then they're giving you, in the next bit, the graph that shows the student's results. Now you can see the graph results go from 0 voltage to 12. So when they varied the voltage, yeah, the dependent variable was the current. Okay, and how do you vary the voltage? You vary the voltage using the variable resistor. Now if you did it in the reverse directions, that means if you put the cell the other way around, or the power pack the other way around, so instead of going towards a positive voltage, you go towards a negative voltage, you'll get exactly the same shape curve, but in reverse. Okay? So you get the shape of this curve would go like this, and it will end in the position where you need this for part 2. You see the voltage here, whatever it is, 12. And the current here, I was going to say, the current at the maximum current at the top will be the same as the current here in the reverse direction. Okay? So you have to make sure that you get this level of detail correctly when you're drawing that, and that comes in part 2. Yes? Alright, so I've already done part 2, and you'll see when we go and read it. Okay. Now they want to see if you know your equations. Now they give you an equation list, or they have done for the past few years, and they said they're going to continue for the next few years. So you've got to state the formula linking charge, current, and time. Okay? So charge is always in Q. Q is measured in coulombs. Current is always I, measured in amps. And T is measured in seconds, time. Now you can see I put an arrow from the word to the letter, so the examiner doesn't think, the examiner won't think I don't know my symbols. They normally give you a mark if you get the correct symbols, if you use the correct symbols. However, it's safer to write a word equation, okay? But you see the way I overcome it is I just put an arrow from Q to charge, okay? Now, if they're giving you the equation sheet again this year, maybe they'll have fewer questions like this where they ask you to just state the formula, because obviously the formula is given to you on a sheet, you just have to find it. So maybe they'll go straight into questions like part 2, which says determine the current in the lamp when the voltage across the lamp is 10 volts. Yes? So you've got to do that from the graph. Okay, so you've got to go to the graph and look for 10 volts. And 10 volts is where I've labeled it here. There's your 10 volts. So 10 volts is there. So you've got to draw a ruler up there. That'll be 10 volts again. So 10 volts is the point there. And then you look across and you'll see the current for 10 volts will be here, and you got to read it accurately. So what would it be? It's one line below the thick line. Yes. So the thick line would be 0.5. So it's 1/5 between, so it's 0.48. Okay. So the current here is 0.48. Okay. And then you've got to put that as your answer here. And if you've shown it on your graph, then that's the working, but it's only 1 mark, so you don't need to. You just got to make sure you know how to do that. All right. So the next part says calculate the charge transferred, that's Q, from the lamp in 30 seconds. So you're now going to use the equation which we looked at before. This equation, I'm rewriting it for the sake of completion. And you can see equation, numbers in. You get 1 mark for putting your numbers in. Yeah. And 1 mark for getting your answer correct. So 0.48 times 30, what is that? So it's 0.5 times 30. So you'll have to look at the mark scheme. I haven't got a calculator on me right now. And then you've got to put the units. So it's 1 mark for the units. 1 mark for putting numbers in, 1 mark for getting the correct answer, and that's how you get your 3 marks. Okay, we'll have a look at the mark scheme and see what it was. Okay, but if you can put those values into the calculator, you'll put it in. Okay, you'll get the mark. Okay, the next part of the question is about energy transfer. Okay, so when you're looking at energy transfer, they want you to calculate the time this time for the lamp to transfer 250 joules of energy, when the voltage that we looked at across the lamp is 10 volts. Okay, so we know the voltage is 10 volts. Now energy transfer is actually voltage times current times time. Yeah? And you want to find time. Okay, so first of all I thought you could use charge, but you can't. So this method that I put here, that's wrong. So ignore that and use this bit. Okay, so you put energy like that, but you want to work out time. So if you put time as the subject of the equation, it will mean energy is at the top. Yeah, energy is at the top in the triangle, and voltage and current are below it. So it's energy equal over voltage multiplied by current. Okay. So this is a more complicated question mathematically, because it has 4 variables in the equation. So they've given us the energy. So the energy goes in there, 250. And then the voltage we knew was 10. And the current we calculated earlier was 0.48. So it's really just using the same values in a new equation. And this will allow you to work out the time to 3 significant figures as 52.1, but you can round it up, yeah, to 2 significant figures, because if you look at it, all the data provided is only known to 2 significant figures. Okay, but they'll accept either of these as your final mark. So 1 for putting the numbers in, yeah, 1 for rearranging the equation perhaps. So 1 for the number, 1 for rearranging the equation correctly, and so on, because obviously rearranging the equation is a skill. The next question. The student disconnects the cell and reconnects it with the terminals reversed, which is the one I did, the reverse. If you reverse the voltage, reverse the terminals to the cell, the voltage will be the other way around. You can then complete the graph like I did, yeah, to show how the current in the lamp will be in the opposite direction as well, as it varies with voltage across the lamp. Okay, when the cell is connected in with the terminals reversed. So we said the voltage is pushing the current in the reverse direction. So what you're looking for to get the 2 marks is that it's the same shape graph exactly, but in reverse. Okay, so it goes down instead of up, and it finishes at 12 volts and minus 0.5 amps. Minus 12 volts I should have written. So that should say minus 12 volts. So both of these are minus, and the other thing you've got to be aware of is that they both start at the origin, and you see the way I did it. Yeah, I started at the origin, okay? So I've started at the origin, I've gone exactly the same shape, and I finished in the same position, okay? So I think mine is accurate enough to get the 2 marks. Okay, now part C is going into using an AC power supply. An AC power supply looks like this instead of having a DC power supply where one is positive and the other is negative. So what does AC mean? Alternating current. Okay, so the student replaces the filament lamp with what? A light-dependent LED diode. Light-dependent diode. And replaces the cell with an alternating current power supply. Yeah? As shown in the diagram. Okay? The student also removes the ammeter and the voltmeter, so we don't need to know the values, but they're going to observe what happens. So, this is the LED. The arrows coming out show that it's emitting light, so that's the light emitting diode. Now, diodes only let current flow when it's in the direction of the funnel, if you like. It looks a bit like a funnel, doesn't it? So the current can only flow in this direction, but this is constantly changing direction. So when the current is going in the reverse direction, let's say if the current's going in the red direction, it will not be able to go through. Yeah? So this will not be possible. So that is not possible. I'm going to take that away because it looks like a voltmeter. Okay? So the current can only go through when the voltage is positive, if you like. So it's in the positive direction or in the same direction as the diode. So the current can only go through, think of this as an arrow. The current can only go through when it's in the direction of this triangle. Okay? Has to go in that way. So that means only half of the time will it be able to get through the LED. Okay? The rest of the time it will be blocked. It's like a one-way street, as we said. Okay, explain why the LED then flashes on and off in this circuit. Now you've got to be able to put that into words and get 2 marks from it. So I put LED allows current to flow one way only. So you've got to put it in clear sentences. Remember, I've taught my students that to get the marks, you have to have the correct amount of depth and detail, and you've got to put things in English in a clear way. So depth, detail, clarity. Now this shows that the current changes direction every half cycle. Yeah? So I'm putting it in words, but I'm saying it to you. And that's what you've got to do. Take my videos, understand what I'm saying, and then you put it into words, and then you can see against the mark scheme how many marks you got. Okay? So it's the explanations in the videos that takes the time, and it's the explanations that gets you to a higher level of understanding. The LED, therefore, lights, because it emits light, when the current is in the forward direction or in the correct direction. Okay? And when it's in the reverse direction, if you want to drive the point home to the examiner, you would say when it's in reverse direction, the LED will not light, so therefore it flashes on and off. Okay? When it's in the correct direction, it's on. When it's in the incorrect direction, it's off. So any of these bullet points will get you one of the marks. Okay? And then you could write, and when it's in the reverse direction, it will not come on. So the total for this question is 14 marks. So electricity is a big topic. Okay. All right. So here's the mark scheme. So I'm going to let you stop the video whenever you want to and have a look at what it's looking for. There you go. The answer that I didn't calculate in the earlier part was the charge is the current times the time, which comes to exactly 14.4. And you can put it to 14 because the data is only known to 2 significant figures, and then the unit was coulombs. Okay? And there's the rest of that question and the LED question, which we just went through, part C. Okay? All right, so that's question 7 done. And then we're going to go straight into question 8. So you can see that question 8 is about a star, because I know this is a star's name. And they want you to understand that stars, the color of the star, depends on its surface temperature. Okay? So basically, they're asking a question about it. And then they're doing such a common question, which is star formation or the evolution of stars. The 6th marker coming up in part B, where it starts as a nebula, becomes a protostar. Then it has its main life as the main sequence star, where it's fusing hydrogen, And then if it's a high mass star like Regal obviously is, then it will become a red supergiant, and then it will explode because it's a massive star, Regal. It will explode as a supernova explosion and potentially become a neutron star, where the atomic structure is not able to withstand the gravitational field of the core that is the remnant of the supernova explosion. And it basically, the atom collapses into the nucleus, so the electrons kind of get captured by the protons, and it becomes like one giant nucleus made of only neutrons, which is a very strange phenomena. So its density will be huge. It'll be like something like 10 to the 17 kilograms per meter cubed. So density will be about 10 to the 17 kilograms per meter cubed. Huge density. Now, they've mentioned here in the mark scheme that they will accept black hole, but the more likely end of a large star when it runs out of fuel to fuse, it will die in a supernova explosion, where it kicks out the external part of the star and then kicks in, if you like, the core, which becomes the dense part. It's less likely to become a black hole. And that's even larger stars could end up, even the neutrons can't withstand the force of gravity when there's a black hole, and they can collapse into what's called a singularity, which means the volume becomes effectively zero, which is amazing. So it becomes like a vacuum cleaner for space, and it sucks everything close by into it. But then for a low mass star, like Sirius, so it's only 2 times the size of our sun, it will also go through the same evolution. When it runs out of fusion material, hydrogen, it becomes a red giant rather than a super red giant. So for both stars, the initial part, the first 3 marks are for both large and small stars. And then they differentiated for Regal, and then here for Sirius, that instead of it becoming a neutron star, it will eventually become a white dwarf, which is white because it's still hot. So it's white hot. Eventually it radiates all its heat into the space, and it will get darker. But when it initially explodes, the core becomes dense, but not as dense as a neutron star, and the outside part, the plasma in the exterior part of the star, will be kicked out into space and form a new nebula. Okay, so I hope that explains, just by looking at the mark scheme, what this question is about. It's only 8 marks, and it's from topic 8, Astrophysics. Okay, so let's see what the wording of the question is. So first of all, they give you a table, and it gives information about 4 stars, and we just went through Sirius, which has 2 solar masses, and it will kind of follow the same path that our sun is going to follow, and Regal, which has 21 solar masses. Now you can also notice that the color of the star is blue over here, and Sirius is blue-white. And the color of the star, you've got to explain how the color of the star is linked to the surface temperature. So which one do you think will have the highest surface temperature? Well, the highest surface temperature is Regal, because it's blue, and blue is actually hotter surface temperature than blue-white. So the color indicates the surface temperature. That's the 2 marks. So 1 mark for working out that regal is the hottest, and the second for explaining that the colour is linked to the surface temperature. So if you like, here I've drawn a table showing you how the colour matches the surface temperature approximately. Okay, so the colour versus the temperature in degrees centigrade or Kelvin doesn't really matter, because remember the only difference is 273, and for these temperatures the 273 is insignificant. So blue will be about 30,000 Kelvin. The white ones will be 10,000, yeah, and blue-white will be in between 10 and 30,000. So the two we're looking at, the two brightest ones, are Sirius and Regal, yeah. Now this one, actually I love the name of this one, is Betelgeuse. It's a red colour, which is cooler, and that's because it's, although it's massive, it's in the red giant phase of its life. It's a super red giant, okay, or a red supergiant, okay, and their temperatures are much lower. So you can see for the red ones, their temperature is only around 3,000 Kelvin. Okay, so that explains how colour is linked to the surface temperature. And here's the bit where I showed you. You've got to discuss the evolution of stars, and they want you to look at Regal, which was 17 solar masses, and Sirius, which is 2 solar masses, MS being the solar masses. So both stars go through, as I said, the nebula protostars as it's gravitationally collapsing, and when the temperature becomes hot enough, then the main sequence part of the life of the stars is triggered by nuclear fusion, yeah? So you could put nuclear fusion, again, depth, detail, and clarity is what we want. For the low mass Sirius, or the lower mass Sirius, is twice the mass of our sun. Our sun's pretty ordinary, average star, and the Sirius, 2 solar masses, like our sun, it will go through the red giant phase, and then when it runs out of hydrogen and helium, it won't be able to maintain the density and the pressure and the temperature to fuse either of those. It will explode, but not in a supernova explosion, just in a kind of normal, let's say, if there is such a thing as normal in astrophysics. And then it kicks out the external gases and kicks in the white dwarf. So this is the core. The core becomes the white dwarf. The external bits are kicked out and become nebula. So I suppose you could add that. And then for the high mass, for the high mass stars, and Regal was really high mass, 17 solar masses, it will become a bit like the Betelgeuse one. It'll turn into a supergiant, a red supergiant, because its temperature drops, and its temperature drops because it actually expands, and therefore, if you like, the heat is spread out over a larger area, and temperature is the average temperature of the surface is cooled down by the expansion. So then it will die when it runs out of hydrogen, helium, and possibly larger nuclei to fuse, and that's a massive explosion, kicks out the external shell, and it will leave the core as a neutron star. So the core will become a neutron star in this case. Okay, and possibly a black hole at a certain mass. There is the likelihood of it becoming a black hole. So this is a very common question that you need to prepare for. And once you know all the different phases, it's like an easy 6 marks guaranteed if they give you another 6-mark question like this. All right, well, I hope you find this video useful. And again, please, just to show your appreciation, with the YouTube, the way it works is it doesn't get seen by other students if you don't like it and share it and create some positivity about it. So if you found the video useful, don't forget to leave a comment giving me feedback. If there's anything if you'd like me to do the rest of this paper, just put a comment in there. Tell me where you're from, yeah, country, etc. And I will try to answer most of the comments when I see them. Okay, so hopefully see you in the next video. Bye for now.